Welcome learners. In today's lecture, we are going to conclude the lecture series by looking into the final chapter of this course, that is chapter number 7, talking about the steady magnetic fields from the 9th edition of our main textbook by William Haight and John A. Buck. We are going to have a look at a brief introduction about this chapter. Then we are going to look into the Biot-Savart law, and then we are going to solve a few problems associated with this law. So let us look at what the chapter is saying in the introduction. So at this point we have learned about, or we can say we have familiarized ourselves with the concept of fields. We accepted the experimental law and its outcome given by the Coulomb's forces, or we can say the Coulomb's law was the first starting point of this lecture series, where we accepted that if we have two charges, the force between them can be represented by Coulomb's equation of Q1 Q2 divided by R square with a constant of proportionality as K. From this relationship among two energy sources, which are charges for this course, we also then move towards finding the electric field intensity, where we said that electric field intensity is nothing but the force acting on a test charge as Qt in the presence of another charge with the unit of volts per meter. And once we understood this vector quantity of the electric field intensity, then we worked our way towards different sources of electric fields. The first one was for the line charge, which is represented with the value of rho of L. Then we talked about the surface charge, continuous source having the variable rho of S. Then we talked about the volume charge, continuous source with rho v, and we also talked about system of discrete charges where we had a point charge at our disposal, which was plus q. For all these scenarios, we figured out the electric field equations for all, where a sample of equation for a point charge was q divided by 4 pi epsilon into r square. So this represented the equation for the point charge, and for the continuous charges we had the integral, let's say for a line charge, rho of L dl divided by 4 pi epsilon r square. And if we had a volume charge, then it was a triple integral, and for the surface charge we had a double integral. For the electric field equation, where the value of this line charge is 2 pi epsilon, for the volume we had 4 pi epsilon r square, for the surface we had 2 by epsilon, again with the value of rho s, rho v, and then with their differential elements as ds and dv. So these were equations for all the electric field intensities for the continuous sources of charges. Now once we have this idea, we now move into the second part of this course, which is talking about the magnetic fields, and especially those which are having a steady behavior. So these are not time changing charges, these are static charges that form these steady magnetic fields. So for this we'll look into few things, that what is a magnetic field, then we are going to see what happens when a current flows or current carrying conductor affects this magnetic field, what is the effect on other sources from the generated magnetic field. Again, keeping in mind that everything will be in the steady state, or the charges will be electro or statics, as we mentioned in the electrostatic field. So this is a brief introduction about this chapter and what we have learned so far. So moving on, we first start with what are the sources of magnetic fields, and then we are going to look at some of the relationships that exist for these equations. So we first start with the sources of magnetic field. So there are three known sources. There are more than that, but let's add an additional one, and we say there are four sources. The first is we have a permanent magnet as seen over here. So this is a natural source of magnetic field. Then we can have a line or time varying electric field. So here you can see that the red ones are the electric fields, and in turn they produce the magnetic field shown over here, but they are varying with time. And then we have a DC current flowing through a conductor. So normally it is known as a current carrying conductor. So if the current is moving in the upward direction, the magnetic field, here it is represented as magnetic flux density B, is going to be generated in a closed loop around this conductor. And we have discussed this, and you probably have heard about the Ampere's law, which defines the third portion. So normally in this chapter we are going to focus the source of magnetic field to be a DC current or a direct current. And then fourth option that exists naturally is the magnetic field of the celestial bodies, which means all the planets in our solar system are also source or a huge source of magnetic fields. So these are the sources, and as I mentioned in this book, or specifically in this chapter, we will focus the source coming from a direct or a DC current. Okay, another thing that we want to know is, or to establish, is some of the relationships that we are accepting when we are talking about magnetic field. Why we are accepting this? Because the equations have already been proven when we talked about the electrostatics field. Here we are going to look into those equations already proven and adapt them for the magnetic field. For example, we talked, or we looked, or we proved this relationship of electric flux density relating with electric field intensity. So here the unit of electric flux density was Coulomb per meter square, and electric field intensity was volts per meter, where this is the permittivity of the material, where we already saw that this permittivity can be broken down to its absolute permittivity and relative permittivity. Similarly, we can say, based on this relationship of the electric field intensity and electric flux density, that the magnetic field will have the same relationship, where we can say that the magnetic field density represented as V is also equal to mu multiplied with the magnetic field intensity, which is represented as H. So here the unit of H will be amperes per meter. Magnetic flux density is normally represented as Tesla with the sign T, and mu is again divided into mu naught and mu r, where in most of the cases mu naught is the permeability, having the value of 4 pi into 10 raised to power minus 7 Henry per meter, and mu r is taken as 1 for non-magnetic media or material. So these are the values associated with the relationship of the magnetic flux with magnetic field intensity, similar to electric flux D with electric field intensity E. Another thing that we want to use, or we want to accept, is we talked about electric flux in the chapter of electrostatics, which was equal to the total charge enclosed by any closed surface. In the similar way, we are going to talk about magnetic flux, which will be equal to the total magnetic field or magnetic flux density stored in a certain region. So this we'll see at the end of our lecture or in the coming series, but we accept that these two relationships are talking about the same thing in terms of the analysis. So these are the equations that we want to, or these are the relationships that we want to take when moving forward with our topics from chapter number 7. Final thing that we want to know is, with respect to the current book, there is some sign conventions that we are going to accept. So what are those sign conventions? The convention is where the current is moving and how the magnetic fields are revolving around the current carrying conductor. So let's say if I have this current carrying conductor and I have a certain area or a sheet, another we have the same sheet. So if the current is moving in the upward direction, In the other scenario, the current is moving in the downward direction. So we apply the right hand rule, where the thumb points towards the flow of current and the curled finger points towards the rotation of the magnetic field. So if the current is moving in the upward direction, the magnetic field will be formed as a closed loop around it as per Ampere's law, and the magnetic field will be in the counterclockwise direction. So the current will move in the counterclockwise direction. And for this instance, a symbol is represented by this book, which means that the current is leaving the page or the sheet or the screen, and it is represented as X. Similarly, if the current is moving in the downward direction, so the right hand rule says the thumb points to the downward direction, magnetic field which is formed as a closed loop will be now moving in the clockwise direction. So this is the clockwise direction, and we say that the current is entering into the page or into the screen, so it is represented by a dot. So this is the convention which the textbook by Hayth and Buck is utilizing, and we are going to stick to the same. So if the current is moving downward, we say magnetic field is in the clockwise direction. So we represent magnetic field with H, and here it is the counterclockwise or anti-clockwise, whatever you like, counterclockwise direction for the magnetic field H. So this corresponds to this position and this corresponds to this position. So these are some of the relationships and the sign conventions that we are going to follow for this chapter. Now let's move to the first law that gives us the mathematical expression of the magnetic field intensity outside any conductor. So this law is known as Biot-Savart Law. This was discovered or presented in the year 1820 by two scientists, Biot and Savart. They were basically professors in France and also students of Ampere law. So that's why you see some similarity of their analysis with the Ampere's law. This law is sometimes known as the current element of Ampere's law. So it is also known as current element of Ampere's law. So what this law is, let us first look into this definition of this law and then we'll understand it numerically. So the definition is a huge one. It's a mouthful, as they say, almost reaching 150 words. But we say that let us assume a current is flowing in a differential vector element length on a filament represented by dl. Then the law states that at any point P, the magnitude of the magnetic field intensity, which is H, produced by the differential element is proportional to the product of the current, the magnitude of the differential length, and the sine angle between the filament and the line connecting the point P at which the field is desired. And we also keep in mind that the magnitude of the magnetic field intensity is inversely proportional to the square of distance, which is the inverse square law, r square, from the differential element to the point P. So the direction of the magnetic field in this scenario is always normal to the plane containing the differential filament and the line drawn from the filament to the point P. There could be two possible scenarios in which the direction could be progressing, and it is according to the right hand thumb rule or the right hand screw turn from dl through the smaller angle to the line from the filament P. So the constant of proportionality over here is 1 by 4 pi. So all these statements in the definition at this point, you shouldn't understand this because we are going to understand it, can be represented mathematically and visually through this image. So basically the idea is that we have a point P which is outside the conductor, and we want to find how much magnetic field intensity is available over here through numerically, and the source is this small filament over here, which they called as the differential element or differential current element. And through this all the definition has been derived. So let's understand it better. So I'm going to draw the image again and then we can do our analysis. Let us take a filament. So this is the starting point of the wire and it goes, let's say, towards this point. So this is termed as a differential current element, or we say it's a filament. filament of certain length. Why it's a filament? Because you take any cylinder and you make sure its radius is almost approaching to a smaller value or almost approaching to zero. So when the radius becomes small and small, it becomes a very thin line, which we technically call as a filament. And this is also known as a differential current element because the current I is flowing inside this small filament, and since the value of I is so small and the radius is so less that some of the times you can measure the current in some portion, some of the time the current vanishes. So we say that this is a differential current element, again meaning that the current vanishes in certain areas, so it becomes a filament. Now in this flow of current we select that portion where the current is normally found, and we say this is the differential length or vector length dl, and this is now going to act as our source. So this portion is our source where the current is normally identified or detected from. So outside of this filament we select a point, let us say this is our point P, where we want to find how much magnetic field intensity is produced. So this is our focal point or the point of interest. So the definition says that, or before going to the definition, let us complete the experimental visualization. So we draw an imaginary line perpendicular from the filament towards the point of interest, which is P, and we say that the distance covered, this line is represented by vector R, its component is AR, and we say that this imaginary line, which is always perpendicular originating from the filament or the differential length or differential current element, will make an angle theta, which is sine of theta over here. So this is the complete visual representation of what? Of this definition that we have seen. So what the definition is saying now, let's complete it mathematically so that we can write it. So the definition says that if we want to find, so let us say mathematically, let's write mathematically the definition. So mathematically, if we want to find the magnetic field intensity at any point, why I'm writing d of h? Because we have selected a smaller region d of l, so that's why the magnetic field at this point will be d of h. So the magnetic field intensity that we want to find at point P is directly proportional to the product of the current flowing in the filament multiplied with the smaller section or vector length dl, which is as a source, multiplied with the sine angle, which is sine theta, made by the imaginary line drawn perpendicular from the filament towards the point P, having an inverse square distance relationship, which is going to be r square. So this is the mathematical representation in free space. So this equation is always in free space. So this is what the mathematical representation is of the previous definition that we have seen. We can further simplify this equation by focusing on dl sine theta. I know that the angle made over here sine theta, or the imaginary line and the filament are making a 90-degree angle, or they are 90-degree apart. So if we have two angles that are 90-degree apart or two vectors that are 90-degree apart, we can represent it by the cross product. So I can say that dl, and taking a cross product is the component of distance vector ar, is represented as the magnitude of the first element, magnitude of the second element with the sine theta. Since this is a unit vector, its value will be 1, so I can write it as dl sine theta. So this dl sine theta can be replaced by this entity, where now my equation simplifies to dh is directly proportional to I dl sine theta can be written as dl with the cross product of the unit vector a of r divided by the distance r square. In order to get rid of this constant of proportionality, I can say dh is equal to 1 divided by 4 pi. So this is the last element discussed in the definition, that constant of proportionality is 1 by 4 pi, and we know because normally in free space we are taking sphere as a coordinate system, so it also represents the sphere. So this is 1 by 4 pi I dl cross product of unit vector and divided by r square. So this is the complete or simplified expression of how to find the magnetic field intensity outside the conductor, where in this case this magnetic field is found at point P and the unit is amperes per meter. So this is the equation that we have. We can further simplify it by introducing the subscripts to this. So we are finding, let's say if this is point 2 and the source is at point 1. So we can further simplify it that we are finding the magnetic field intensity at point 2, where the source is I1 dl1, the distance vector is r12 and the unit vector is r12. So this is what we can do in terms of the direction. So once this is known, we can find the effect of the current or a total current moving inside the filament. So the total current from this could be, so if you want to find the total current or the total magnetic field as the effect of the total current I, we know that we can just integrate this. So the total magnetic field now is equal to, we have a closed loop line integral of I d of L cross product of AR unit vector divided by 4 pi r square. So this is now the integral form of the equation, and the first one was the differential form of the equation. So that completes the explanation of the Biot-Savart law. Moving on, we can also have other applications, or we can find the Biot-Savart law, or we can find the magnetic field intensity using the Biot-Savart law if the nature of the object changes. So in the previous case, our nature was a small filament. So this was a very thin filament. What if we have a object that is a volumetric object, and also if we have a surface or a sheet of surface, then what could be the magnetic field intensity? So again, we don't want to go into the proof of this, but we can stick to certain equations. So Biot-Savart law can be applied. So if we take the example of the volumetric representation, or if you want to find the magnetic field intensity outside any point of a volume, so the equation is such. You can use this equation that the magnetic field intensity is going to be the volume integral of what? So in the previous equation where we had IDL, we replace the IDL with JdV and JdS. So what it means is I'll replace IDL with J cross product of AR with volume divided by 4 pi r square. So this is basically now the current density that has been introduced. Why? Because we have studied that if the current is moving inside any volume, that current in a specific region can be represented as the current density, where current density is the current per unit area or per unit surface. So this is now the expression to find the magnetic field intensity, where IDL in the Biot-Savart law equation has been replaced by J dV. Similarly, if I have a surface sheet, so the IDL in previous equation will be replaced by K with D of S differential element. What is K? K is basically a surface current density. So if I have a surface sheet over here and the current density is moving normal to it on the surface sheet, so K is basically going to be the current that is available on the front of the sheet or on the width of the sheet. So this is basically the width section of the sheet, which is basically B. So the current is now equal to the surface current density K and multiplied with the width B. So in this scenario, the magnetic field intensity for the sheet is going to be the surface integral. You replace I dl with K cross product of AR along D of S divided by 4 pi r square. That's it. So we don't want to go into the proof of these equations, but these equations should be known to you whenever the object or the geometry changes. So once these equations are known, let us look at an example and see how we can find the magnetic field intensity using the Biot-Savart law. So let us say we have this question, or we have this example to begin with. So we say find the incremental field strength. So the incremental field strength is something that is changing, and since we are talking about magnetic field, so it is the magnetic field strength. So find the incremental field strength at point 2 due to the current element. So due to the current element. So what does current element means? It is basically IDL. So we represent the current element because this is the current moving in a small vector length. IDL is having a value of 2 pi along A of Z with the unit of microampere meter at point P1. So at point P1. So it means, so let us try to understand and plot this first. So we have these points. So at point P1 is at 400 and point P2 is at 030. We want to find what is the magnetic field at point P2 due to P1, and the current element is along the z-axis. So if I want to visualize this, it means that if I draw the axis, so this is my y-axis, x-axis and z-axis, and let us see what we can draw. So the first point, so this is the origin. The first point is somewhat over here. So this is P1 with the value of 4, 0 and 0, and the second point is P2. It is at 030. So we now want to know where is the line element. Line element is along IZ, so we say it is parallel along z-axis. So this is our differential current element. Differential current element. And this is now the source at point V1. So let us connect the line perpendicular from the source towards point P2. We know then this distance according to Biot-Savart law is the distance vector R, and the unit vector could be AR, and it is going to make a certain angle theta, and we need to find what is the differential current magnetic field at this point. So this is the visualization of the differential current element acting as a source parallel to the z-axis, and we want to find the magnetic field intensity at point P2. So in order to solve this, we know from the Biot-Savart law that the magnetic field intensity is equal to I. So let us use the subscripts. So if this is 0.2, this is 0.1, so I want to find the magnetic field intensity at 0.2, where the current is moving in I1 dl1 cross product with the unit vector 1 2 divided by 4 pi r square. Again it is unit vector from 1 to 2. So this is the expression, let's call it A, which we want to find. So we have the value of ID1, which is 2 pi. Don't forget this micro 10 to the power minus 6, and we need to find what is the unit vector AR. So let's first start with the unit vector. So we can find AR12 as the distance vector divided by its modulus, R12 and R12. So what is the distance vector? Is the difference of 0.2 minus 0.1 is the distance vector R. So the 0.2 is 0 minus 4, so it is equal to minus 4 along A of x, then 3 minus 0 plus 3 along A of y, and then 0 minus 0 is 0. And then we take its magnitude, which means we are going to take the square of the first value plus square of the second value. So it comes out to be minus 4A of x plus 3A of y divided by 5. So this is the unit vector's value that we are getting for this scenario. Now let us see what else is needed. So we have figured out the unit vector in equation A. R in the denominator is also figured out, and the current element I1 dl1 is also given. Now we need to figure out the cross product or the numerator part of equation A. So we need to basically do what? We need to do the cross product of the current element I1 dl1 along with the unit vector AR12. This means we can use the determinant method to find the cross product. So as it is along rectangular coordinate system, so we are going to have A of x, A of y, A of z, the components of ax and ay and az for id1. So it is going to be 0, 0, and then we have 2 pi into 10 raised to power minus 6 because only the z component is given. Then for the unit vector, we'll have minus 4 by 5, 3 by 5, and then 0. So this is the matrix that we have formed, and then we can apply the determinant of it, which means, let us do it over here. So first along a of x, the value comes out to be, so for the a of x, this and this is ignored and we take the product and difference of these two values. So it comes out to be minus 3 by 5 multiplied with 2 pi into 10 raised to power minus 6. Then we go for a of y. So it is going to be, for the a of y, we take these values. So it is going to be the product of this with this. I'll bring the negative sign out, so it will be minus a of y. It will be 4 by 5 multiplied by 2 pi into 10 raised to power minus 6. And then for a of z, it is normally 0 because we are going to block this and this portion, so it is automatically 0. This means my output comes out to be, once you solve these values, is going to be minus 3.769 along a of x minus 5.026 along a of y, and don't forget the micro value, that is into 10 raised to power minus 6. So this is basically the solution to the cross product or the determinant. Now once we have all these things, we just incorporate everything into equation A. So from equation A, our final output comes out to be that the magnetic field intensity is going to be, so we take this minus 3.769 a of x minus 5.026 a of y with a value of 10 raised to power minus 6 and divided by 4 into 3.14, which is the value of pi, into, so you take the square of 5, so it becomes 25 as r square, and then the final answer comes out to be minus 11.9 along a of x minus 15.9 along a of y, and this is in, so, nano ampere meter. So this is the answer to this example, or how we solve finding the magnetic field intensity. So this concludes this example. Hope you got the idea. Moving on, now let us find the applications where we can utilize this Biot-Savart law and figure out how we can find it for various sources or filaments. So the first application is, we want to find the magnetic field intensity when we have an infinite filament and finite filament. So again, this is the final equation that we will get, but how we got or reached to this equation, let us understand from this image, or let me draw it over here. So we want to figure out, or the topic is the application, or how to find the magnetic field. So let's say we need to find the magnetic field of infinite, this is the first case, infinite current filament. So this is the first, and then we'll also look into the equation, not the proof, of the finite current filament. So let us first draw the scenario and then we apply the Biot-Savart law. So again, we go to the easiest of the coordinate systems. So we start with the cylindrical coordinate system, because the filament is a cylinder with the radius approaching to 0. So normally we can say that this represents x, y, and z, but our analysis will be in the cylindrical coordinate system. And we say that our filament is lying on the z-axis. So this is an infinite long filament. It is from minus infinity to plus infinity, and I'm just taking this portion. So the filament is along minus infinity to plus infinity, okay, infinite long filament. And then we say that the current is moving in the upward direction on this filament, so the direction of the current is along z-axis with the unit vector a of z. We select a small differential length which is acting as a source. This is d of L, and we again, as per Biot-Savart law, select point 2 to be our target. So this is point 1, the source as per small differential length, and P2 is the point. So we always draw a perpendicular from the line towards the point of interest. So let us say this is our perpendicular line. Again, this will represent it as the distance vector AR, and we can have the unit vector AR, or the component of distance vector R. The distance from origin to point P2 along the y-axis is represented as R, and the other way around for the current can be represented as R dash. So the distance vector is now basically R minus R dash. So we can say distance from this point. So since this is a cylindrical coordinate system, because filament is cylinder, we can say that the value of R is only the radial component, which can be represented by rho along A of rho. The Z value is not varying, so it is just having a value of Z8, and there is no rotation for point 2. This means phi is equal to 0. So we can say that phi and Z are not varying. So there is no variation on these axes, only the radial component exists. Radial component exists, and that is from origin to point P over here. So this is the radial component that is existing. So once the source and the target fields have been created, let us see if we can find the magnetic field intensity at point P2 using the Biot-Savart law. So therefore the magnetic field intensity for this scenario, we start with the Biot-Savart law, which is d of H is equal to the differential current element, which is a product of IDL cross product with the unit vector AR divided by 4 pi r square. Now what is unit vector in this case? So the unit vector in this case comes out to be, so A of R is the difference of R minus R dash, or 0.2 minus 0.1. So it is going to be rho A rho minus Z A of Z, and the magnitude of these elements, which is rho square plus Z square. So this is the value of a unit vector. We can also represent dl in its differential components or along z-axis as dz along a of z. So these are the two things that we can use. So this can be represented along d of z as well. So incorporating everything into the Biot-Savart law, we can say now that dh at point 2 is equal to I. Then I can replace d of L with d of z along a of z. Again, this is I1. Then we have the cross product of the unit vector, that is rho a rho minus z a of z, and then we can divide it by 4 pi. Now r square can be represented in the form of cube, so I can write this as rho square plus z square with the power of 3 by 2. Again, why we can do this? Because we know that the unit vector's definition is r divided by r absolute, and this comes out to be square. Sorry, this is a single value. It gets multiplied with this square, so you can change the power to 3 by 2. So this is basically the small amount of current, let's say equation 1, that is existing for an infinite long conductor. It is existing outside this infinite long conductor. So we want to know what is the total magnetic field, which means we need to integrate this. So for the total magnetic field, we say that H2 is going to be the line integral of I dz along a of z cross product with rho along a of rho minus z along a of z divided by 4 pi, and then you have rho square z square 3 by 2. So now what is this line? So this line is along z axis from minus infinity to plus infinity. So now we just integrate this. We know that the coefficients will be taken out since the integration is along z axis. So the coefficients will be I and divided by 4 pi. What we can do is, if we look at the cross product of unit vectors a of z with a of rho, it will give us a of phi, and then the cross product, so this will give us a of phi, and the cross product of az with az will be equal to 0. So then the coefficient rho can be taken out as well, and we'll be left with minus infinity to plus infinity. The value will be d of z with a phi divided by rho square plus z square with the power of 3 by 2. So this is the simplified values before the integration. Now if you look at the integration, this is an indefinite integral. So this is an indefinite integral. Again, we can use the tabulated data to solve this, and if you look at the table, the value of this indefinite integral comes out to be such. So I'll write the coefficients a rho divided by 4 pi, and we'll bring the a phi outside, and we'll be left with z of z divided by rho square, and then in bracket we can have rho square plus z square, and then the limits will be from minus infinity to plus infinity. So this is the solution of the indefinite integral. So once we solve this integral, final equation comes out to be, after you put in the integrals, it will be I with rho divided by 4 pi, and after the limits are put in, 2 divided by rho square along a of phi. You cancel this 2 with 2, and rho cancels with the power, so you are left with I divided by 2 pi rho along a of phi, and that is the final expression in amperes per meter for the magnetic field or the total magnetic field intensity existing outside an infinite current carrying filament and conductor. And if you look at this unit vector, it makes sense. Why it makes sense? Because if we go back to our image, we can see that the current is moving in the upward direction. So if we apply the right hand thumb rule, which means the thumb is pointing in the upward direction, then the magnetic field which is going to be formed over here, magnetic field, as you can see, will be moving in the counterclockwise or anti-clockwise direction, as shown over here. And if we look at the cylindrical coordinates, what is this motion between x and y, and then if it goes beyond, it is in the phi domain. So the unit vector a phi is also confirming our mathematical proof that if the current is moving in the upward direction, right hand rule says the magnetic field move in the counterclockwise direction or along a of phi. Now let us come to the second proof of the magnetic field when we have source as a finite conductor. So the second application is if we have source as a finite length conductor or filament. So we don't want to go into the proof of it, we'll just write the equation and understand a few things associated with it. And what is that thing? So again, let us draw the filament. Let us use this side now. So we have the coordinate systems. We start with x, y and z, and this time our filament is of a certain length. Let's say it's above the origin. So this is the filament. We give it a certain point, let's say z1, and the top point is z2, and then we select a small differential length as a source point. So this is the d of L. Let's say this is point 1, or we say this is our source. Again, our point of interest or the target is along the y-axis at point 2. Originating in the cylindrical coordinate systems is the radial distance. Let's say r is equal to rho a rho. This is the radial component. We join the value from the source perpendicular to this point P2. We say this is the distance vector r, and it is making a certain angle alpha over here. So now this is the arrangement of this image, and the mathematical expression that we get for such is that, without going into the proof, if you want to find the magnetic field at point 2, so the total magnetic field at point 2 comes out to be I divided by 4 pi rho sine alpha 2 minus sine alpha 1. Again, the magnetic field is moving in the a phi direction with the unit of amperes per meter. So this is the mathematical expression. Now, with this mathematical expression, we are now introduced to two new things, and those two new things are the alpha 2 and alpha 1. So where is alpha 1 and alpha 2? If we look at the infinite conductor, we can see we introduced two variables z1 and z2, which will help us design these angles. So always take the value of 1 at the lower end of the conductor, which is z1, and higher end is represented as z2. So if we connect from the lower end towards the point of interest, the angle formed in this case will be alpha 1. So let us say this is alpha 1, and if we connect the higher point to this point, the angle formed will be alpha 2. So from these angles we can solve the equation for finding the magnetic field intensity. Now how to choose the values, or let us say the signs of angles. So this is a trick that you can use. So what could be the value of alpha, whether it will be positive or negative? So for this we look at three scenarios. Let us say these are the three conditions where we can have the finite conductor. So the first scenario, our conductor is over here. The second scenario, it can be over here. The third scenario, it can cover this section. So what are these lines? So before we talk about these lines, let us point the lower and higher ends of the conductor. So lower end is always given as 1, higher as 2. Same goes for 1, same goes for 2, and for the third part as well. Now these lines are basically those points where we want to find the magnetic field. Let us say point P2, as we have seen in our previous proofs. So in order to find those points, we always consider this line as our reference line. Reference line being that this is the perpendicular line which we are drawing from the source towards the point of interest where we want to find the magnetic field intensity. So these are all our reference line. In this case, we can say that this is an origin because the element is above that line, this is below it, and it is covering certain portions of the top side and the bottom side. Now once we have these lines, let us take the first scenario where we can draw the point from 1 and 2 towards the point. So this angle comes out to be alpha 1 since it is coming from point 1, and this comes out to be alpha 2. Since both the alphas are above the origin or above the reference line, here the angles will be positive. Similarly, we draw the points from 1 and 2. So we can say that this is alpha 1 and this is alpha 2. Since both the angles are below the reference line, so we will have negative signs for the angles. And obviously for the last case, one angle is below the reference line. This is alpha 1 and this is alpha 2. So here alpha 2 will have a positive sign and alpha 1 will have a negative sign. So these are the tricks that you can use to figure out the signs of alphas when utilized for finding the magnetic field intensity when the source is a finite length conductor. Now let us look at an example and better understand these angles signs. So in this question we have been given, or we have been asked to determine the magnetic field intensity at point 2. Let us say point 2 is located over here and the current flowing through it is 8 ampere. The current is distributed such a way that it is directed inward from infinity to the origin on the positive x-axis. So we can say that this is extended towards infinity and this is our origin. So the first current directed is 8 amps. So we can say that this portion is a finite conductor from positive infinity towards 0, we can say this is conductor number 1, a finite conductor. Then the second is that the current is now outward from to infinity along y-axis. So if we extend this, this is positive y-axis to positive infinity and origin towards positive infinity. So let me change the color for this. So this is now the second conductor that we have, and it is moving from origin towards positive infinity along the y-axis. So let me say this is my finite conductor number 2. And we need to find the magnetic field intensity at point P2. So we know that we have two conductors, so I can say I can use the superposition principle to find the total current. The total current is found in such a way, so I can say that I need to find, so if I start with the solution, I need to find the total current HT, which is going to be the sum of the first conductor, let me call it along x-axis, and the sum of the second conductor magnetic fields along the y-axis. So this is what I want to find, and I can say that this is my h1x and this is my h2y. So let's find the magnetic field individually and then add them together as per superposition principle. Now in doing so, the final equation for this h of t, so this h of t will be, or the individual h1x and h2y will be incorporated into the equation of the finite conductor, which is I divided by 4 pi rho sine of alpha 2 minus sine of alpha 1. So this is the equation that is going to be utilized for finding h1x and h2y. In this case, that will give me the total magnetic field. So let us first start with the first conductor, or let's use the same scheme. So this is my conductor number 1, and I want to find, as per equation here, what is the magnetic field along x. So my equation will be h1 of x is equal to I divided by 4 pi rho sine of alpha 2 minus sine of alpha 1, and this is should be along a5, but we will also confirm it as well. So in order to find this, let us see what are the angles that are given to us. So if this is point P, we said we always draw a perpendicular line from the source, in this case which is along x-axis. So this is my x-axis, this is my z-axis, and this is y-axis. So from the source, perpendicular is drawn towards point P. This is making an angle 90 degrees. Now if this is my reference line, as we saw in the previous case, this is my reference line which was shown over here, and it is going from the source towards point P2. So if this is the reference line, where are the angles alpha 1x and alpha 2x? So I need to first give the values of 1 and 2 to this finite conductor. So let us say the lowest point will be at positive infinity. If I extend this point towards infinity, we know we cannot join infinity to point P1, but let us assume this is my lowest point of the finite element and this is my highest point of the conductor. So this is my highest point, this is lowest point. So if I join this lowest point to the highest point, I can say that instead of infinity, this is my first value over here. So this is the point of the lowest value, because this is going towards positive infinity, so I can have point 1 or lower point anywhere. So I've taken this point which is now perpendicular towards point 2, and from the top side or from the origin, this is my second point. So the alpha that is joined to the second is shown over here. This is alpha 2, and if I extend this positive x-axis in parallel to this point, this is my alpha 1. So now I can immediately see that for the reference line, alpha 1x is having a value of 90, but it is going to be positive 90 over here. But since the point is below, so I am going to say this is negative, because alpha is below this reference line, so the angle will be negative 90. Now what about alpha 2x? So in order to find alpha 2x, I'm going to focus on this triangle, which is this portion. So if I look at this triangle, I can say that it is forming, or I can use the trigonometric identities which we have discussed, that to, ka, to, a. And here I am going to use the tangent theta to solve this. So I can see that my hypotenuse is the side over here, and the angle which is closest to this is my adjacent, and this becomes the opposite. So tangent theta for alpha 2, tangent alpha 2x is equal to opposite over adjacent, which is equal to opposite is having a value of what? So if I look along the x-axis, the point along the x-axis is having a value of 0.4. So this is x, this is y, and this is z. So if I go along the x-axis, this is having a value of 0.4. So this is 0.4 divided by adjacent is along x-axis in this direction. So sorry, along y-axis, or it is parallel to the y-axis. It is parallel to the y-axis. It is 0.3. So this means alpha 2x is going to be tangent inverse 0.4 divided by 0.3, and it comes out to be 53.13 degrees. So this is the alpha which I got. So hence my h1x comes out to be, if I use equation number A, the value of current is 8 divided by 4 into 3.14. Now what is the value of rho? So if you look at rho is going to have a value of this one. So if we are creating a parallel line that is moving from, or the vertical line that is initiating from the source and going towards point P2, this is what we term as a radial component. And since this is parallel to y-axis, so the value will be 0.3 for rho. So it comes out to be 0.3. And what is the value of sine? So the sine value will be sine of alpha 2, which is 53.13, minus sine of minus 90. So once you solve all these values, the answer comes out to be 3.8197, and this is along A of phi. So this is the first solution to the first finite element. Now this is the answer in amperes per meter. So if we are asked to transform this A of 5 into Cartesian coordinate systems, we can easily say that the answer will come out to be, stick with me for this one, minus 3.8197 along A of z. Now why we got this negative along A of z? Because if we look at the magnetic field, why? Because this H1 represents magnetic field. So if the current is moving in this direction as per the right hand thumb rule, curling our fingers will be moving towards the anti-clockwise direction. This means that the current will move in this direction. So this is the direction of the current. Since we are talking about this region, so the magnetic field will touch the negative z of axis over here if we were in the conversion system. So without doing the transformation from one coordinate into other, we can immediately say that magnetic field will touch the negative along A of z. So this is one way of converting the signal from cylindrical coordinates into rectangular coordinates, and this is just to let you know, but our answer is sufficient over here. If you are asked to represent the answer in the rectangular coordinate, then you have to use this value. So again, summarizing this, we basically utilized the previous scenario of finding the sines of the angle by looking at the reference line and where the angle is. If the angle is above the reference line, we take the sines value as positive. It is below, we take it negative, and it is in between, then we decide where it is. So from here, if this was our reference line, alpha was below this, that's why we took minus 90. Why 90? Because we are always drawing a perpendicular from the source towards the point of interest, which is P2. And for the second alpha 2, we use the geometric equation of tangent theta to get the answer. Now let's find the solution to the second cylinder, which is H2 of y. So again, for H2 of y, let me use the other side. So now we want to find H2 of Y, the magnetic field's effect for the second conductor. The equation remains the same, which is for the finite conductor I divided by 4 pi rho sine of alpha 2 minus sine of alpha 1, and it is along the A phi. So in order to find the values of sine, we go back to the image, and now we focus on the second conductor over here. So we again say that this is the point 1 starting from the origin, and it can go to the point 2, and we can select any point because it is going towards positive infinity. Let's say we selected this point as the second point. So for this, our point is going to be, so if we connect point 2 to the point of interest P2, this is the first point, and if we extend this along to positive infinity, so the angle made from Y to this infinity is alpha 2y, and now this is our reference line. So in our reference line, we can see that the value of alpha 2 is coming out to be positive 90, because this is always going to be a perpendicular of 90 degree, and this is on the positive side of the axis. It is going towards positive infinity. That's why the value will be positive 90. So we can say that alpha 2y is coming out to be positive 90 because it is near to the positive infinity value, or it is above the reference line. What about alpha 1y? So if we go back, alpha 1y is the same point as it was in the previous case where it was 2. So this is, again, I'm just highlighting it. It is alpha 1y, and this is the angle made. So if we flip the image, this is below point or the reference line, so it is going to be a negative value. This is for sure. But what is going to be the value? So now this is my triangle where I'm going to apply the tangent rule to find the value. Again, this remains our hypotenuse. So if this is our hypotenuse, the angle here becomes adjacent, and this is now my opposite. So what is the value of the adjacent of the opposite? So if we look at the value of adjacent, it is parallel to the x-axis. So if it is parallel to x-axis, the value will be 0.3 or 0.4. We'll see with the image. So let us write for the tangent theta. So for alpha 1y, I can say applying tangent 1y is going to be again over opposite to adjacent, following the rule. So we can say alpha 1y is equal to tangent inverse. Now what is opposite and what is adjacent? So the opposite value is along x-axis. So we can say that this is parallel to y-axis. So the value of this will be 0.3, and adjacent is parallel to x-axis, which will be 0.4. So the equation comes out to be 0.3 divided by 0.4, and this equals to be 36.869 degree. But since this point is below the reference line, it is going to be a negative value. This is my alpha 1y. Now once I have everything, we incorporate this into our equation. For h2y comes out to be, current is going to be 8 divided by 4 pi. What is the value of rho? So we go back, the value of rho. So the radial line is now this one. This is rho from point 2 to point. So this is my rho, and I can see this is parallel to the x-axis over here. So the value will be 0.4. So the rho value is going to be 0.4, and then you have sine minus 36.86 for sine alpha 2 minus sine of 90 degree along A of phi. So once we solve this, we get the answer of 2.546 along A of phi. This is H2 of phi. Now if we have again this answer in phi and we transform it into, let's say, Cartesian coordinates, so we can say that A phi is again going to be minus A of z. Why? Because now we want to see what is the magnetic field varying towards. So again, if this is the current carrying conductor, then as per right hand rule, the magnetic field should be like this, in this direction. So this is again touching the z-axis or negative z-axis. So that's why we have the negative z-axis, which means the answer of H to Y can be minus 2.546 along A of Z amperes per meter. Again, this is for your information. Now, once we have both of these solutions with us for H1 of X and H2 of Y, we can just conclude the answer from the first equation 1. So just add both of them together. So the final current, or the total magnetic field, sorry, comes out to be H1 of X plus H2 of Y, which in the phi coordinates comes out to be 2. So the value is 3.817, 3.8197 plus 2.546, which comes out to be 6.3657 along A of phi. And if you want the answer in A of Z, so this is the answer in A of phi. In A of Z, it is going to be minus 6.3657 along A of Z. So this is the answer that we are getting in the phi coordinate systems and the A of Z if you are asked to find this answer. So that concludes the solution. Hope you got the understanding of the angles or how the values of the sine angles are figured out. Moving on, let us look at few more examples and see how we can find the magnetic field. So in the first problem, we are given the value of P1, P2 and the differential current element, and we need to find the magnetic field intensity for parts A, B and C. So we have already seen a similar example in the beginning of this lecture that corresponds to part A and part B. Let's focus on the third part. So let us see how can we solve this, because now the value is having 3 coordinates. So let us find the solution to the first question. So solution to drill problem 7.1. So let me write the values over here. It is, we need to find delta H2 for P1, P2 and IL, where the values are such. So the what has been given to us, so we need to find delta H2, which is equal to delta or dH2. This is what needs to be figured out for point 1, that is at 1, 2, 3, for point 2 at minus 3, minus 1 and 2, and the differential current element IDL or delta L is 2 pi minus AX plus AY plus 2AZ. So I1 delta L1 is equal to 2 pi minus A of X plus A of Y plus 2 along A of Z volts per meter. Sorry, this is current, so it is going to have microampere meter. Okay, and need to find delta H2. So we need to find it at point 2 or point 1. Given the following values for P1 and calculate delta at H2. So this is at point 2. Okay, so we know by Biot-Savart law that delta H2, which can also be written as dH2, is equal to I1 dL1 cross product of AR12, which is the unit vector, divided by 4 pi R12 square. So this is the equation that we want to use. So let us call this equation A. Now again, we want to figure out what is the unit vector in this. So let me use this side. So the unit vector A12 is going to be the distance vector by its magnitude. So the distance vector is, you just differentiate P2 minus P1. So minus 3 minus 1 minus 1. So it is minus 4 A of X. Then you have minus 1 plus 2. So it is going to be minus 3AY and then minus A of Z. So this is the distance vector that we are getting from P1 to P2. So then once we have this, what is the magnitude? Divided by magnitude is coming out to be you take the square of 4 square, 3 square and 1 square, so it is coming out to be 5.099. so this is the unit vector, that's the difference of p1 minus p2. Now once we have this, we can move on by inputting the values. So the next thing we can do is find the I and dl1. So what is I dl1? So let me use this portion. So I1 delta L1. So I1 is 2 pi in this equation. So we can simplify this. Let us say 2 into 3.18 is 6.283 along a of x with a negative sign. Then you have plus 6.283 along a of y, and then you have plus so you multiply 2 pi with 2, and there is 6 into 2 12. This is 0.566 along a of z. So this is basically simplified version of current element, and don't forget the micro value minus 6 that is given to us. Now let us take the cross product of equation A. So we take I1 dl1 cross product of AR1 2, which comes out to be, since this is Cartesian coordinate systems, AX, AY and A of z, where AX for ID1 is equal to minus 6.283, 6.283 for Y, and 12.566. Don't forget micro value 10 to the minus 6. And for AR2, so this is I can simplify it even further. So this unit vector minus 4 divided by 5.09 comes out to be minus 0.7844 along A of x, then minus 0.5883 along A of y, and the third comes out to be minus 1.961 along A of z. So this is the simplified version of the unit vector. Let me enclose it in a box so we don't get any confusion. So here it comes out to be minus 0.7844 minus 0.5833 and minus 0.1961. So this is minus 0.1961. Okay, so this is the matrix, and then we can find the determinant quite easily out of this. So I'm just going to write the answer of the determinant. You can do this, we have done this before. It comes out to be 6.1604 along A of x minus 10.48 along A of y, and then you have plus 8.624, and everything gets multiplied with the micro value over here. Thus this is basically answer of the cross product of IDL1 into the unit vector. Now DH2, what we wanted to find, comes out to be, you just incorporate everything and divide by 4 pi r square. Again the value of r is 5, so you take square of this. So the answer comes out to be 18.9 along A of x minus 33.9 along A of y plus 26.4 along A of z, and this is nano ampere per meter. And this is the solution, or the magnetic field intensity that was required from us, especially for the third part. So A and B we have already seen, so we have just solved the third part for understanding. Now let us come to the last question of this lecture, that is drill problem 7.2. We have a current carrying 15 amperes of current in the AZ direction. It lies along the Z axis. We need to find H in the rectangular coordinate systems at point A and point B. So let us see what could be the solution for this. So now solution for drill 7.2, this is a straightforward problem. So we need to find the magnetic field intensity. Let me first draw the scenario. So this is the rectangular coordinate systems along y, x and z. Our current, so basically our source is along z-axis, so the current, let's say it's over here. You just need to see whether this is a finite conductor or an infinite. I think it's an infinite. So a current carrying filament 15 ampere in the AZ direction along the entire z-axis. The entire z-axis means it's an infinite long. Okay, so this is an infinite long filament. Okay, that's good. So the current moving here is 15 amps in the upward direction. So we can say that the point is okay in the upward direction. This is from minus infinity to plus infinity. And what else we have? We want to locate the point, so the point A and B. Okay, so for the point 1 or point A, this point is lying at under root 20 0 0 4. So this is under root 20 0 and 4. So this means Z is at 4. So for the line we can say that Z is at 4 and the point might be over here. Let's say this is point A. So under root 20 0 and 4, and again this is making a 90-degree angle over here. So we know that the magnetic field intensity for an infinite line is I divided by 2 pi rho, and this is along A of phi. So the current is 15 divided by 2 into 3.14. What is the value of rho? So the rho is the radial element that is moving from this towards point A, and we needed to find the magnetic field at point A. So this is what we wanted to find. So this means that this is my rho, which is basically under root 20 0 and 4. So it is under root 20. This is my rho along A of phi. So once we solve this, it comes out to be 0.5338 along A of phi. So this is the magnetic field intensity that is going to exist around this. And if we draw this magnetic field intensity, so if the current is moving in the upward direction, right hand thumb rule says the magnetic field will be moving in the anti-clockwise direction. So if we move from the A phi into the rectangular coordinate system, magnetic field is touching the y-axis. So it is going to be 0.5338 along A of y amperes per meter. So our answer needs to be in the coordinate system, which is the rectangular coordinate systems. We can see that if the current is moving in the upward direction, magnetic field is moving in the y-axis. So this is answer to the first part. Now let us look at the second part, where the point for the second part is given as 2 minus 4 and 4, and we need to find the magnetic field intensity. So this is 2 minus 4 and 4, and we need to find this at point B. So again the equation remains the same. So our point is basically how to find the rho. So if we plot this again for point P of B, this is x, y and z, we can say that point B is lying somewhere over here, where the point is 2 minus 4 and 4. So let us say this is 2 minus 4 and 4 with z. So the angle made is 90 degrees. So in this case we need to figure out what is this rho. So the rho then comes out to be the distance vector from this point to point A. Again at this point it can be 0, 0 and 4. So the value of distance vector, or the value of rho, is basically value of r, which is 2ax minus 4ay, and z coordinate comes out to be 0. So this is the perpendicular distance from this point. So if we take the magnitude of this value, then it comes out to be 4.472, and that is the value for rho. So then equation comes out to be 15 divided by 2 into 3.14, and this is 4.472 along A of phi. Once we solve this, it comes out to be 0.5338 along A of phi. So this is the answer that we are getting. Now once we have this answer, we need to convert this into the Cartesian coordinate systems. So since we cannot transform it visually, we have to utilize the transformation matrix, where the Cartesian comes out to be h of x along a of x, h of y along a of y, plus h of z along h of z. And once you do this, so value of h of x is the component along a of x, and for y and z it remains the same, similar to what we have seen in the second chapter. So once you do this, the Cartesian output, I'm going to write it here for you, you can try. The solution comes out to be 4.7 along a of x plus 0.239 along a of y amperes per meter. So this is the solution converted or transformed from the cylindrical coordinates to the Cartesian coordinate systems. And why we are doing this? Because now we have two values to deal with, that is the rho, phi, and z cancels out because 4 and 4 will be 0. So once you have two values of the x's, then you have to use the transformation. If you have only one value, as we saw in the first part of this problem, you can just visualize it to get the answer in the rectangular coordinate system. And this concludes our today's extensive lecture.